This video covers the several different kinds of waves that we'll talk about in this class. So first there are mechanical waves, which are waves that can be described using Newton's laws. A good indication of mechanical wave is that if you see a wave occurring, it is most likely a mechanical wave. And an example of a mechanical wave are like water waves. So second, there are electromagnetic waves, which we covered at the end of our magnetism unit. Electromagnetic waves cannot be described using Newton's laws. So next we're going to talk about transverse waves, which are waves where the particles' motion are perpendicular to the wave's motion. So let's assume that we have a wave traveling down a string here. The particles in the string must move up and down in order for this wave to propagate, which looks like it would be going to the right. So this kind of looks like the wave spectators make at sporting events. The individual people move up and down, but the overall wave travels throughout the stadium. So next we're going to talk about longitudinal waves. Longitudinal waves are when the particle's motion is parallel to the wave of the motion. A compressed spring is a great example of longitudinal waves. The spring loops move in the same direction as the overall wave. An example of a longitudinal wave is a bunch of people standing in line with little space between them. So if someone pushes the person standing in front of them, the next person in line would then stumble, and the following people in the line would stumble, assuming everyone can regain their standing position. This is what a longitudinal wave would look like with people. The go-to example for longitudinal waves are also sound waves, and sound waves are propagated by areas of high and low pressure. Finally, we're going to talk about two different other kinds of waves. So there's a pulse, which is when the medium particles are excited briefly before returning to equilibrium. So this is kind of like if you were to throw a rock into the water or shout a single word. There's also something called a periodic wave, and that's when medium particles are continuously excited. So this is like a tuning fork, a guitar string, or ocean waves. Alrighty, so let's assume that we have this wave here. Now let's define a few more terms. The equilibrium position is going to be along the x-axis, and therefore the amplitude of the wave is from the x-axis to the maximum point of displacement, as shown. The wavelength is the distance between two identical parts of the wave, like from a crest to a crest, like here, or from a trough to a trough. This is trough to a trough. Wavelength is represented by the Greek letter lambda. The equation for the velocity of a wave is the wavelength multiplied by the frequency of the wave. Let's do an example. We want to calculate the wavelength for light that has a frequency of 5 times 10 to the 14 hertz, and the velocity of light is 3 times 10 to the 8th meters per second. So we have our velocity of a wave equation, and we can fill in our known values, and when we solve, we see that the wavelength for light is 6 times 10 to the negative 7th meters. You can also be asked to find the time that it takes for this light wave to make one full vibration. So we know that period is equal to 1 over the frequency, and we know that the frequency is 5 times 10 to the 14th hertz, and when we solve, the time to make one full vibration, which is known as the period, is 2 times 10 to the negative 15 seconds.